Okay, cool. So hopefully people online can see a slide deck.
Yeah, it's recording.
Great. Okay, cool.
You can give it a picture. Yeah.
Right, I guess I'll crack on then. Yeah. So yeah, as I said, I'm a data scientist with the Godwin Institute here at the University of Bristol, and I've been doing some natural language processing, a particular process called topic modeling. So I'm going to introduce where I'm like my background, and then I'm going to try and give you guys a crash course, keyword crash, in topic modeling. There's lots of the notes in the slides go into more detail than what I'll talk about today. So I'll share the slide deck afterwards. And so there's random bits where you're like, oh, I wonder what the difference between these two algorithms are. And I'll be like, here's an hour worth of YouTube videos that will explain the difference better than I can in a 40-minute talk. Cool. So just a brief intro of like who the Godwin Institute are. So we're one of the 5 research institutes at the University of Bristol. And the way that we work is that we're like kind of like a pool of fractional postdocs. So if you guys have money and data science problems, then you can cost us out on data science stuff. We also run a free data science help desk that all UOB researchers are entitled to up to a day of support from, called AskJGI. And so you can email AskJGI and be like, hi, can you help me? And it could be, what algorithm should I use for this? Or how do I install Python? Or how do I optimize this code or whatever? And there we can help with that. We also run free training courses in Python and a bit in R as well. We do yearly CCon funding, which is just finished, so it's kind of irrelevant to anyone here at the moment. And then I've been supporting this project with Eunice for the last kind of 3 months at 40% full-time equivalent as just part of like a little. Basically, we weren't busy enough over the summer, so we made ourselves more busy for free. Yeah, cool. And then you can go on our website and find out more, etc. So the project itself is, as I understand it, is a survey to Bristol inhabitants about lived experiences of extreme weather events in Bristol. And some of the survey responses are free text. And so these are kind of questions that are like, how did you adapt to the heat wave in Bristol? And so, for example, someone might say, I would do exercise earlier in the morning when it was cooling. And so what we want to do is some kind of thematic analysis where we pull out topics that people have mentioned throughout this like large amount of free text data and try and understand what are the general themes people are talking about. And so you can do this manually, which Joe Godwin did with the heat data set, but kind of quickly realized it's a lot of hard work and quite annoying. And so it's quite nice if you can have a more reproducible kind of algorithm that you can kind of hit go on and get some rough outputs. So before we dive into like how we do this algorithmically, thinking about how do we topic model by hand. So say you only had 6 free text responses and you're thinking, how might I go about topic modeling? So pulling out themes. And so I think the way that we might intuitively do it is, you read the first one and you kind of go, okay, what is it about this text that's interesting? Maybe you come to this text with some preconceived notions of what you think is important. And so you might go like, okay, I think hydration is an important thing. So every time I see someone mentioning water, I'm going to like make a little tally. Or you might read things and go, oh, okay, actually, I think it's important when people mention closing curtains. And so you start a new tally every time you see something that's more interesting. But you can see that this process, you might read a couple and then realize actually someone mentioning something, like in this set, for example, curtains being closed, I think it's only mentioned once. And so you might decide, actually, that's not worth mentioning, like relevancy-wise, because it only comes up once. And then you might see some sort of miscellaneous answers like see previous answer, which are things you specifically don't want to pick up. And so you can see that this process can be, if you do it by hand, it becomes quite ad hoc and quite hard to reproduce quite quickly. And if you got 2 different people to look through this, or even yourself on a different day when you've forgotten what the data looks like, you'd probably come up with 2 different answers. So it's in our interest to do something that's reproducible and something you do on scale as well. And so that's why automating topic modeling is quite a good thing to do. So as a general like idea of when we might do topic modeling, more data / documents, as I might refer to them, is usually better, as with kind of a lot of data analysis. So for the survey responses we were looking at, we were on the order of between 1,000 and 4,000 individual responses from people. And if I'm honest, that's kind of the lower bound. And so if you have less data than that, you should just do it by hand. And then you should also think about like diversity of topics, right? If you only think there's 3 topics of interest, then you probably need a lot less data for you to start being able to pull out those topics. But if there's lots of different topics, then you need to start being more considerate of like of how much is coming up there. Shorter sentences are easy to interpret, and I'll explain kind of intuitively why that's the case in a bit. And then also how standard the language is in your text is also a factor. So for example, if there's lots of different slang, that could be a factor. And in particular, if there's sometimes slang and sometimes not, then there's more variety in your language. That can be a problem. And then also if there's like responses in different languages, that can be something. And the topic model that I'm going to explain has capacity to do topic modeling in different languages if you wanted to. And then, just to share an example, and I think in the notes for the slides is also their archive paper here, but there was an example of a project where some people funded by JGI did an analysis of medical influencers talking about COVID-19 on Twitter, and they analyzed 424,000 tweets. And so that's the kind of scale where you start feeling, one, it's completely unreasonable to ask some poor PhD student to do that manually, and 2, you start feeling quite happy about some kind of validity in results just because of the scale. Right?
You looked much at the similar literature during extreme events when some of the stuff has been done for that as well, right?
I've not looked too much at it. I'm trying to think what stuff that we saw initially. I think the thing is with lots of extreme event stuff, there was either quantitative stuff or it was qualitative. And so I think topic modeling is in this sort of sweet spot in the middle where it doesn't replace qualitative analysis. It's almost like exploratory data analysis for text. And so I think a lot of the survey data is, at least from the studies I've seen, has been like a lower number, like the stuff we're working with. But no, I haven't found specifically for extreme weather events if someone's done something similar for tweets, say about heat waves. But I think that'd be quite an interesting thing to do.
I think there have been papers about tweets about extreme weather, but I don't know if they used topic modeling.
Topic modeling,
yeah.
But it's like sentiment analysis.
Yeah,
Right,
it's all the sentiment stuff.
Yeah.
And the Lancet uses it a lot, but there's definitely a few published papers on it. But yeah, I have no idea if it's topic modeling or how they do that.
Yeah.
Be interesting to know, I guess.
Yeah, I will. I'll let you know in a week or so. Cool. Okay, so we're going to use a method called BERTopic modeling. So topic modeling's been around for about 20 years. And the main method people used before is called LDA, latent Dirichlet allocation. So in older literature, you're more likely to see that kind of analysis pop up. It's pretty good. It's kind of a Bayesian statisticsy method. Please don't ask me to explain how it works on the spot, particularly with a statistician in the room. But all the cool kids are using BERTopic these days, and this relies a bit on the kind of pre-trained sentence transformers that are present in tools like large language models and stuff like that. Because the BERTopic method is quite new, if you're using any like code assist things like GitHub Copilot or ChatGPT, they'll be rubbish at writing code for this because their training data is not old enough to have actually like figured out how to do it. The good news though is that the documentation for BERTopic is extremely comprehensive, and so I basically was able to teach myself how to do this just by reading the documentation. So that's the link to it there. I would highly recommend reading through it quite thoroughly. Cool. So there's a kind of 6-step process, and I'm just going to like talk through that process as we go. And again, if you have questions about any of the steps in the middle, please do ask and interrupt me. Okay, so there's a step 0 with all data analysis where you have to pre-process the data. BERTopic takes a list of strings as its input, and so this is and so these strings are usually like sentences or something or phrases about, say in this case, our adaptation to cold weather events is the data I've got loaded here. And so you need to remove all your empty entries because, as I'll explain in the next step, the processing works better when the sentences are shorter. It's quite hard to like pull out multiple bits of context for one sentence. It makes sense to split sentences into smaller sort of sub-sentences, if you like. So in the data processing, what I was doing is I was splitting by things like full stops, commas, dashes, the word and semicolons, which are the main things I found in the survey data, where people would write a thing and then write like semicolon, another thing. And so I split these into separate responses, but I wrote some code, and I'll share the GitHub as well. I wrote some code that basically like kept track of the index. So if person 1 said a sentence that was actually split into 6 different things, you can keep track of actually only one person talked about these 6 things. Occasionally people would talk about kind of the same thing twice. And so it's useful to reflect on the difference between the number of times a topic was mentioned versus the number of people who mentioned a topic. So you can see for this, the length after all the splitting is about 3,000 sentences. And so here's some like examples. And so some of them are longer, and then some of them are like curtains closed, right? Because we're literally splitting by commas. And sometimes you might want to play around with how much you split by, depending on, so if you're looking at tweets, for example, or if you're looking at, let's say, abstracts for papers, you might decide that actually it's worth not splitting stuff, or even splitting by more conjunction words like or whatever. So pre-processing, as with all data science, you kind of got to do it. Okay, step 1, now we get onto the actual natural language stuff. BERTopic works well because we, as people who do like data science and machine learning, are bad at looking at text in like large quantities, but we're quite good at doing numerical analysis of large quantities. So what we do is we convert our sentences into numerical representations. So this is like a bit abstract, so I'm going to try and give some examples and some explainers. So BERTopic has some like pre-built-in sentence transformers that you can use. And so you basically put in your text data, and for each one of your sentences, it will output a vector in some large dimensional space, which you can just think of as like a long list of numbers. There's a really great YouTuber called 3 Blue 1 Brown, who's I've stolen some screenshots from some of his videos in the next few slides. Has a really lovely video in explaining the intuition in the context of ChatGPT, but it's the same kind of embedding systems. So what we're doing is we're embedding, in our case, sentences instead of just words. And we're taking a sentence and transforming it into some high dimensional vector. And so you can understand that the longer the sentence is, the more complex stuff is in it. And so the more difficult it is to cram all that information into some large vector. And so that's why it makes sense for us to split our documents into smaller sub-sentences. And so when we're in this like large dimensional vector space, different directions in the space have some kind of associations with certain like sentiment or meaning extracted from the training data, right? My slide just froze. Cool. Which means sometimes there is encoded biases. So you may have like heard about this when ChatGPT 3 was first launched, and people would do like word problems where they were like, the doctor did this and the nurse did this, which one's the woman? And it would more likely say the nurse is the woman based on biases in training data. And so whilst I didn't encounter this problem for any of the work we were doing here, something to keep in mind is that some of the like associations that are embedded might not be ones that you want. But often they're quite useful and insightful. But that's just something to keep in mind.
So exactly what is the training data, I guess, is the question.
It depends on which sentence transformer you're using. And so there's different ones. So this one I used is kind of the default recommended in the BERTopic recommendation, which works well with the English language. But then there's another one here that is good for lots of different languages as once. I can't produce you a list of documents and tell you what the answer is, but I'll show some examples that hopefully will illustrate it a little bit better in a sec. So these examples are taken from that YouTube video I mentioned, and they are embeddings of words. They're sort of representations of embeddings of words, not sentences, but I think it gives the same intuition. So if we look at, E brackets of a thing is like the embedding of that word. So what does the vector look like when I embed the word man? And then, so what we're seeing here is that when we embed the word uncle, and we look at the difference between that and the embedding of the word aunt, there's some distance vector here. And it looks like it's quite similar to the embedding vector between man and woman, which is essentially telling us that when we go in kind of that direction up and down in our vector space, we're encoding something about gender, right? And so you'll start seeing that different directions in our vector space will encode information. However, because sometimes words have multiple meanings, which means that you need to be careful with context. So if we look at say king and queen here, because queen has other associations other than just like leading monarch who is a female. So like drag queen or queen like music, there will be kind of some offset here. So, and these are, in this case, probably not biases I wanted, but they're kind of built in the data. So there's still like a decent an idea that like, obviously this is a much compressed view, but somehow like down on the y-axis is associated with like to a different gender, but it's kind of offset because of other confounds and stuff like that. Does that kind of explain your question a little bit more?
Yeah, well, presumably these things are much more than two-dimensional.
Yes, so BERT's sentence embedder is 384 dimensions. So this is just like a representation. ChatGPT 3's is like 12,000. So, but BERT is, I ran all of this on my machine and it was like nothing took more than a minute. Like when I was rerunning the model with Eunice, you'd be like, oh, can you change this? And it'd be like hit run and be like, so how's your week been? So, and it's not like, okay, I've got to queue up a HPC job or whatever.
I mean, I'm sure there's a lot, you know, because we have a lot of issues in climate science with multi-dimensional data. And the minute you try and do something like with a matrix, like try and invert it or something.
Oh, yeah.
As soon as it's sort of 4 dimensions or higher, that becomes incredibly difficult.
Yeah.
But presumably these guys have solved all of this.
The next step is dimensionality reduction, so I'll talk about that in a bit.
Yeah.
And one other fun example from the video is where someone has looked at the embedding for the word Japan and the embedding for the word Germany, and then looked at the embedding for the word sushi and the embedding for the word bratwurst, and found that the differences kind of line up. So there's some also direction about like nationality or country, and some other direction about like food and relevant associations there. So obviously these are compressed representations, but you get this idea that we're quite good now at turning text into numbers in a way that the numbers, the coherence between the two is somewhat maintained. Right? And now we just have a exploratory data analysis problem, but with high dimensional vectors, and we're better at that. Right? So step 2 is we want to cluster these documents, right? Because we're looking for like themes where stuff gets grouped together. So we want to clusterize our vectors. But as Dan kind of mentioned, when you're in a high dimensional space, you can run into problems. So as I mentioned, the default embedder that I've used for this, for BERT, is 384 dimensions. And so it's recommended that when we do certain like density-based clustering methods, that we do some kind of dimensionality reduction. You can skip this step, and BERT's very modular and very accommodating, but I basically wouldn't recommend it. It doesn't take really any extra time. If you're familiar with the cursor dimensionality, that's kind of why we need to do this dimensionality reduction stuff. And I found a really cool blog about like high dimensional geometry, which is out of the scope for this talk, but kind of fun. So feel free to read about that.
Yeah, put that in the Slack if you would.
I mean, I'm going to share the whole slide deck. I've got loads of different links and everything, but yeah, I'll share those. So BERTopic is very modular, so you can tell it, actually, I want to use, I like using principal component analysis for my dimensionality reduction, so I'd like to use that instead, and you can just tell it to do that, and it will do that. And that's all good. So in case the idea of dimensionality reduction is a bit abstract to some people, I wasn't sure sort of the different expertise in the room. I cooked up an example. This is in the JGI office, which is on the whiteboard. So on the left-hand side, we have a 3-dimensional problem, I guess. Each red little stick figure is a person in an office. And so we want to understand that there are different directions in my vector space are associated with different things. So let's say, for example, that the more senior people are on the higher floors, and so their sort of Y value is higher up. And then let's say the sunlight comes from the right-hand side, so all the data scientists in the building are on the left-hand side to avoid it. And so we have a 3-dimensional space with some features, and I want to reduce this so that I can draw it in a 2-dimensional way. But I still want to preserve information about the different directions that come out. So if I say naively just said, okay, let's just look at the top of the building and just kind of look at where everyone's heads are, you get something like the right-hand side. It's not exactly PCA, but PCA-ish. And so what you see is that you lose all the information about hierarchy because you're just looking down. So now you see that even though there's 3 people here, you've kind of got like 4 and 3 and stuff like that. So you're sort of losing some information there. So you want to reduce dimension in a way where you still preserve information in directions that are relevant to you. And so the way that UMAP works is by trying to join all the points in your space together, and then looking at how close they are, and then when it reproduces this in a lower dimension, it tries to keep some semblance of if points were close together before, they should be close together in my lower dimension as well. So in this case, I've just drawn little sort of bubbles around different groups, and then I've reproduced those so that on the right-hand side are the non-data people, on the left-hand side are the data people, and then higher up in my square, there's the management, and lower down is the more junior members of the team. And yeah, so here's an hour-long video on the difference between UMAP and PCA if that's your thing, and if it's not, all the more power to you. Again, very decently well-written documentation, quite like dense if you're not like familiar with Python. But the main thing that's important when we're defining this model is there's this parameter n neighbors, and this kind of dictates how big we expect. Clusters is probably not the right word I should have used here, but how dense we expect our groupings to be when we reduce our dimension down. Because we want our output to be quite dense for when we do clustering, we kind of want this number to be larger. And so if I show you here, I found this really cute blog, and this is actually like a live like animation but I'm not clever enough to put that in a PowerPoint, so I've just screen grabbed it. But they wrote to the Smithsonian Museum and said, can I have a 3D model of a mammoth, please? And they got 10,000 points for this 3D model. And then this is the output of a 2D UMAP projection with my n neighbors parameters being really small. So you see the points are kind of like quite spread out. And then the model rotates in the live web page. But as you increase the number of neighbors, you start getting like more dense points. So they're all really spread out here, and then they start kind of converging. As I increase the number of neighbors larger and larger, it kind of flattens in some way. It makes it look like someone's like dropped an anvil on a mammoth and just flattened it into the ground, but yeah. Obviously, this is only going from 3 dimensions to 2 dimensions, so it's a lot more like abstract when we're going from, in our case, like 384 dimensions to 5. But you should play around with this n neighbors parameter here. The parameter will vary a bit between data sets, because if I have a really large data set, I can freely set this number very large. But when we found this when we were doing switching between different data sets for the work I was doing with Eunice, is that if you set it too large, then UMAP won't be able to do its job properly, especially if you set the number of neighbors to be larger than the number of documents you have in your data, then it can't do that, right? So it's a fine-tuning thing. But yeah, so it's not vital you understand how UMAP works, but I think a bit of intuition as to why this parameter is important is quite useful. Cool. So step 3 is we've now flattened into like a 5-dimensional space, and we know that some direction is preserved in a way that different directions have meaning. We now want to sort these into clusters. So the default that BERTopic uses is HDB-scan, which is a kind of density-based clustering method. When I was first learning machine learning, I learned k-means clustering. So I thought it was useful to there's distinctions between when one is useful over the other. But essentially, when we're using text embedding data, what we find is that the clusters are not spherical. They're pretty random shapes, different densities and sizes. There's sometimes noisy ones that we kind of don't care about. And you also don't necessarily know how many clusters there are. And then just as a brief demo, so this is stolen from another nice blog I found. So if you look at this and you're like, cool, how many clusters do I think there are? The blog claims there's kind of 6. So there's 1 here, there's this dense line here, 1 here, 1 here, 1 here. So there's 6. So even if I tell k-means clustering, I think there's 6 clusters, it will do a pretty rubbish job. Whereas if I tell HDB-scan, I don't actually have to tell it how many clusters I think it will be. It will just kind of go, oh, I think this is a cluster, this is a cluster. And so we can kind of see in this context where I don't have sort of circular or round, densely packed points, HDB-scan will outperform it every time. You'll also notice that k-means will always force points to be in clusters, which can sometimes be advantageous. But HDB-scan, the N stands for noise. So it will be like, is this a point in a cluster, yes or no? And if it says no, then it will produce like an outlier cluster as well. But yeah. So when we use this model as part of BERTopic, we can indirectly influence how many clusters we have by telling HDB-scan what's the minimum cluster size. And again, for different data sets, we need to tune this for different values. Because if I only have 100 documents, then min cluster size of 50 is going to crash because it's just not going to be able to pack everything in. Sometimes it can be annoying that not all the points get put into clusters and these outlier clusters. So what we actually did is we used HTTP scan, and then afterwards we looked at all the outliers, and then Eunice kind of decided, actually, I think they should go in this cluster, and sort of manually reassigned where appropriate. There are other methods of reducing number of outliers as well, but that was just the one that we felt relied on experience the best.
Much your data.
Cherry picking.
Cherry picking, yeah, something like that. As long as you do it consistently, right?
Yeah, it is interesting. There is decades of literature on a lot of these algorithms about where and when they can be used, and the communities just get really up in arms, don't they? About
Yes, they do. Yeah.
Can't use k-means on this, samples of different sizes,
Yeah,
or things like that. And it's quite interesting, actually.
It's also, so HTTP scan is reasonably recent. UMAP was like 2017 or something. It was outputted. So all those arguments are happening, but like we're still playing catch up. So
yeah, this is actually really interesting. I was unaware of both those two things, and anyone who's had any maths training knows PCA, EOF, k-means, all of that stuff is embedded in every undergraduate
like
maths
SQL
course and physics course.
Yeah.
But none of this stuff is sort of known about because, well, you don't go back and redo a degree, do you?
No.
And even then, I don't know how much would be in a formal degree now on this.
I think when I've helped run coding courses, the focus has been like, here's what you have to write in your Jupyter notebook to make the code run, and less of the intuition of how they work.
Yeah.
And I think knowing a little bit, I mean, I'm like math background, so I find the intuition really interesting. I don't think the intuition is necessary, but like it's helpful when you're running it and something goes wrong, you will immediately be like, oh, well, I've set the cluster size to be too big or something like that. So that can be useful.
Yeah.
So you don't have to go like full maths PhD nerd about it, but like I think knowing a bit about what code you're writing can be quite insightful. Yeah.
But I think your examples where you make the example against k-means is always good, because if anyone knows anything, they'll know k-means.
Yeah.
So that sets the concept, the context.
Yeah. Cool. So step 4 is this thing called bag of words, which is essentially like tokenizing topics. So just to a recap of what we've done, we took our sentences, we did our sort of pre-processing, we turned them into big numbers, we reduced them into like a smaller vector space, and then we sorted them into clusters. And so what you have now is you have all these numbers, these vectors that have been sorted into clusters, and we know that each vector is associated with one sentence. So you can kind of be like, what does cluster 1 look like? And then look at the documents inside it. And so now just imagine a situation where I'd given you a bag of words in this case, and I'd be like, cool, tell me what the themes are of this bag of words, right? And so the bag of words will be bigger than 3 or 4 sentences, but my writing's, I had to write in caps just so you could read it, but my handwriting gets increasingly bad the smaller it gets. But if you think about how would you do this manually, right? You might start looking at one and then be like, oh, okay, well, this one talks a lot about like curtains and blinds, but it also mentions the sun. And this one says sun as well, but it says sun cream. And so maybe just eyeballing it when there's sort of 3 or 4 sentences is easy enough. But now imagine you've got 15 to 20 clusters, and each one of those might have up to like 100, maybe 500 sentences. So we want to think of a way of doing this sort of consistently and automatically, right? And so BERTopic has some methods for that. When we do this, so we've already clustered our documents. When we look for these representation words, it can be helpful to remove some potential candidates preemptively. So you can kind of, so we're now not doing anything to the original documents. We're now using the documents we've clustered as candidates for representations of each of our clusters, but we're going to do some stuff to the representations to sort of narrow down our options. And so the 2 main things that I found useful was removing stop words and including n-grams, and we're going to explain what on earth I mean by that. So in the context of natural language processing, stop words are words that in some sense don't convey meaning, air quotes, about what we're actually talking about. And so if you use for example, Python has the natural language toolkit, which is kind of the most widely used NLP toolkit in Python. And it has a pre-made list of English language stop words. And so I've printed out the first 50 or so here. And so you can see these first ones are like pronouns and stuff like that. And so if I remove these from my bag of words representations, it doesn't really matter for our purposes. it doesn't really matter if someone's saying I or you or they or she or whatever. So now, and also some of the prepositions are kind of less useful. So now this has been reduced to kept curtains closed, blinds, hot keep sun. So it's not perfect, but it's starting to remove unnecessary candidates and narrow things down for us, right? You can choose your own stop words. You can choose to not eliminate any stop words at all. But for example, you could say, if it says see previous question, I don't want that to be a representative. And so you could extend your list of stop words quite easily. The really important thing to note here is that, this actually happened when we first ran the topic model. We ended up with a cluster that was see previous question because lots of people had written that. Quite rightly, we were like, oh, we actually don't want that to be a topic. If we remove see previous question as a potential representation, we don't remove the topic. We now just have a topic where it doesn't have any viable candidates for representation. So you basically just told Python to mute itself and to not say any of these as potential representations. So if you actually do want to not have anything that says see previous question, you need to go back in your pre-processing and remove those candidates entirely. And I'd recommend like making a copy of the original and then keeping track of where you change stuff. But yeah, so we can remove stop words. And then the other thing is n-grams. So everyone's like, what on earth is an n-gram? They're just phrases where n is the number of words in the phrase, right? For example, in the original bag of words I wrote, sometimes I wrote sun cream. I guess all the times sometimes I wrote sun cream as one word, sometimes I wrote it as two. And so you'd want the phrase sun space cream to be a potential representation of your topic. At the moment, it's only looking for representation words, but you can essentially say in Python, you can go, look, if these two words occur next to each other frequently enough, then consider them as a potential single word, right? And so I've outputted some of the bigrams from the two-word phrases from the heat responses. So some of them, like bought fan, curtains closed, drank water, are pretty like intuitive. Some of them are like earlier day con unit, or a little less like, where does that come from, right? So you can arbitrarily have n-grams for as large values of n as you like. Best practices and convention in industry and whatever is that people look for like words, bigrams, and trigrams. But if you were working with data, for example, that was less diverse, and so you were expecting similar combinations to appear more frequently and sometimes longer combinations, say like 4-word phrases, there's no reason why you couldn't extend that range. But for our purposes, I found that n equals 1, 2, and 3 from my n-grams was sufficient to account for. And so when we run this vectorizer model as part of our BERTopic, we tell it what list of stop words to include. We tell it the n-gram range, so in this case, just 1 to 3. And then min df tells us how frequently a word has to be included in my topic before I start considering it as a representation candidate. Because our data set was so small comparatively, I just set this to be 1. So if it occurs once, just consider it. If you had an enormous data set, you could have min df equal to 1, but it might slow things down a bit. So if you say, okay, like make sure it's been mentioned at least 10 times, then it would quickly eliminate lots of like singular words by now. So now we've got some sort of candidates, and we want to like pick out which ones are actually like good candidates, I guess. So now I've eliminated my stop words and kind of considered bigrams and stuff. But what might be some good representations? So I've written down some like suggestions underneath, but how would we like systematically pick this out? And because it's one thing to look at this example where I've got 3 clusters which each have about 4 sentences in, but again, you got say 15 clusters with 200 in each, give or take. What method can you use to consistently pick out good representations? So a word with the asterisk that it could be like a bigram or a trigram or whatever, is a good candidate representation if it appears in a topic lots of times. So for example, like sun cream appears in this one lots of times, but also if it doesn't appear in other topics very often. So the word sun might not be so good for the bottom topic, just because in the top left topic, it also occurs, right? So it's something that's in some sense unique or quite special for a given cluster. You also maybe want to think about like how many words are there on average per topic. So if the topics are much smaller, you'd probably expect a lower number of good representations. Whereas if the average size of a topic is quite large, then then you might want to expect more topics. And so you might rate more words more highly. So someone's already done this, and there's a scary looking formula for it. And I'm not going to go through the formula in a lot of depth, but essentially, so this term here is saying how frequently does the word X or the term X, could be a bigram, whatever, occur in my cluster or class C. So if this number's big, score goes up. And then fx is how frequently does the word occur across all my classes. So if this number's small, then the score goes up. But if this number's really big, then this gets smaller, right? And then we also account for like the average number of words per class. So this is the main way, this CTF, IDF class-based term frequency independent. This is the method that people use in not just BERTopic, but in other topic modeling aspects as well. I've written about it more in the notes for the slide. There are ways, or maybe on the next, so you can fine tune this formula a bit. For example, if you hadn't removed stop words for whatever reason, but you wanted to make sure that if a word occurred way too frequently, you almost like discounted it. So like the word run is like quite semantically, has lots of different meanings in the English language. It might occur in lots of different topics, but meaning different things. You might want to be like, actually, it's occurred too often, and so I just want to disregard that. So you can fine tune this to account for that. There's also ways of fine tuning this to work, or they claim to work better with smaller data sets. I played around with it, didn't really see much of a difference, and decided not to use it. But yeah, so there's methods, there's parameters here that you can change under the hood. I just decided not to use any of them, but I've written about them in the notes for the slide. So now what we've done is that we've taken our sentences, we've made them look like vectors, we've made them look like vectors on a small enough scale, and now we've clustered them into little bags of words. And then for each of the bag of words, we've pulled out a bunch of candidate phrases or words that could be good representations for it. So if we wanted to, we could stop here and be like, here's my representation. But BERT has some methods that you can fine tune the topic representations. There's loads of different methods you can try. You can actually give the representations to ChatGPT. There's like a method in it, and it will just be like, oh, this is how I would describe this topic. But you can, but there's other sort of more simple things that you can do as well. And they're all built in under the hood. They're just sort of different methods you can use. So I played around with a few of them, but the thing that I found most annoying is I'd produce some outputs for Eunice and Joe, and I'd end up with a situation where there would be like, say, a topic where people were talking about like fans and air conditioning, and so there might be some viable topic representations that could be used fans, using fan, use fans. And these are all basically the same, but as far as my embeddings are, they are different. And so actually I wanted to say, well, these are basically the same, so just consider them as one representation for my topic. And so it turns out there's a method for this called maximal marginal relevance. I've decided to not put the equation on the screen, but essentially what it does is it looks at all of your candidate representations that you've generated from the previous step, and then it says like, okay, if these are too similar to each other, then just kind of collapse them into one representation. And so now what you end up with is all of your representations will be sufficiently diverse based on how much you fine tune this diversity parameter here. And so this is the representation method that I used that was kind of fine. Yeah. Cool. So now we should probably like hit go. So the code is reasonably straightforward. So you're just like defining this object as you would like an sklearn model or something like that. And you can like put these parameters in manually, but I mean, I was kind of copying the documentation, sorry. But I found that like actually writing down like each of these parameters gave me a better idea of like, what am I doing? So you initialize the model and then you fit it to your list of strings, your documents, right? And so now you want to see what it looks like. So the first thing is that you can produce like a CSV, like a data frame. So for each document, it will tell you where's it assigned, and then there's lots of information about the topic or the cluster that it's assigned to. And there's another data frame you can output, which is just information about each of the topics. But I guess the most important thing is like, what's the document? What's the topic? What are some of the representations for it? And then you'll see here, I've just written some code that I appended this index so I could keep track of. So in this case, these three things are all said by person number 8. And so we can keep track of that, right? And so when we look at the topic info, again, it's like, okay, what are each of my topics look like? and stuff like that. So this topic -1, you recall the N in HDB scan stands for noise, and so there will be a noise cluster, an outlier cluster. This is not the best run of this. This is when I made the slide deck 2 weeks ago or something. And so you'll see that the outliers are really big here. And so with some fine tuning, the outlier cluster got smaller. But it will treat the outlier cluster as one of the clusters. And so as you can imagine, when you have a bunch of different sentences that are the only thing they have in common is that they don't really have stuff in common with anything else, the representations are going to be quite weird. So there's like stayed home, eating longer, dog, like quite varied representations, not very insightful, but the rest of the clusters are more insightful. And again, what we found is that it was actually quite useful to go through. It was a smaller list than 629, thankfully for Eunice's benefit, but to go through these and be like, actually, I think this corresponds with some of the stuff I've seen in topic 0 or 3 or whatever. Yeah, so we can start visualizing. And so what I found is that the visualization methods for BERTopic are good for diagnostics, but not great for like showing off in like a paper or something. So I'm going to show the diagnostic plots first, and then I'll show like the other plots, some of the other plots that we've made. So this is one of the 2 main diagnostics that I used, and it's essentially for each topic, other than the outlier topic, it will give you like what are the most common representation words. And so lots of these are quite like short. And again, this wasn't the best run that I did. If I'd ran this without the MMR setting, you'd get lots of things where it said like cancel, cancelled, stuff like that, like the same thing repeated. But what you start seeing is like extra bedding, heated duvet, stuff about weather in the garden, transport, driving, things like that. So you shouldn't expect like, because it's sort of exploratory analysis, especially with such a small data set, you shouldn't expect this to have like perfectly sorted things, but it gives you like a nice initial idea. I think the thing that's more useful is the next slide. So the H in HDB scan stands for hierarchical. And so there are methods of visualizing the hierarchies that these clusters fall into. And what this means is that you might decide, actually, for our purposes, I only want 4 big topics. And so you could do something here where you force, you could merge these topics together, or as we were doing, where we were kind of thinking, oh, should we manually reassign something? For some of our plots, we could kind of go like, okay, well, let's look at these 4 clusters and see, do I think these should be the same or some like similar subgroup or something like that? And so basically you run the model lots of times with different parameters and see what this looks like and what this looks like until it starts looking like something that you believe is a good representation for your data. And so the boring, but the plots that I kind of did manually is for each topic, including the outlier at the top, I outputted what is the number of responses per topic. And then arguably more usefully is what is the number of unique people per topic. And so you'll see that these are different numbers, which is quite an important thing to pull out if you're using this sort of splitting method that I was doing. So I think for we've pending, got some like cool like icicle plots, which I've not put in the slide deck, but I'll share once the paper's kind of coming a little bit more. The irony for the icicle plot name was not intended, although a sunburst diagram was used for the lived experiences of heat. So like credit where needed. Yeah, so as I kind of mentioned, with all like machine learning stuff, there's some fine tuning. You're not going to hit run first time and it'll all be perfect. You run it, you visualize the outputs with the diagnostic plots, you tweak the parameters, run again. Luckily, with our size of data set and how efficient BERTopic is, this I don't think took, like I think if I ran my entire Jupyter notebook, it was like less than a minute. So, and I've not got like a super speedy laptop or anything, right? There's stuff you can do. There's lots of other stuff with fine tuning that you can do with BERTopic, which again, read the documentation. But yeah, so I've added other things that you can do slides, and I'll happily answer questions about them if you have questions. But maybe I should stop there so we have time for like more questions. But yeah, I guess the main thing I should highlight is that BERTopic is quite a new tool. So one of the methods that we looked at using called zero-shot modeling was like released after I started working on this project in the last 3 months, which is really cool. But at the same time, this means that the ideas of like best practices and the standards of validation are still kind of developing in this area. So it's a double-edged sword. But yeah, thanks for listening.
Thanks, that's great.
Cool.
Can I ask a quick question?
Yeah, of course.
So I think you mentioned that after the fine tuning. So even if you put in exactly the same parameters, if you did it again,
Yeah.
you get slightly different outputs.
Yeah.
So where does that come from? Is that from the vectors?
So it's not from the vectors, it's from UMAP. So the dimensionality reduction
Right.
has a stochastic element to it,
Okay.
which means that there's some randomness built within it, and so that means that you might, if you run UMAP on the same data set multiple times, you get, even with the same parameters, you could get different outputs.
Okay.
So yeah, that keep in mind. So it's kind of annoying. You hit run and be like, cool, this is perfect. Let's add a bar chart, and then you actually hit run all on the spread on the Jupyter notebook, and then you've got to like, oh, it's not the same. Yeah. But yeah.
It should be similarized, just that using numbers.
Yeah. I think there was someone else in chat. Oh, yeah. No worries, Rian. Thanks. Cool. But yeah, I guess maybe I'll just briefly mention that there's some cool thing, the two cool things that you can do that might be relevant to some of your work. So if you have if your documents, whether like tweets or whatever, have a time element to them, you can map how topic representations change over time with something called dynamic topic modeling. So you do your clustering with all your data, but then you go like, okay, like if I look at a given topic at a given time window, what would the representations look like, say, a year ago, and what would they look like now, and how would that change? And the other thing that we consider doing for this work is something called zero-shot topic modeling. So I mentioned at the beginning, you were doing topic modeling by hand. You might come with some preconceived notions of what the topic could be. And it turns out that BERTopic has a method where you can give it a list of potential topics, and it will kind of try and fit stuff into clusters. And you can basically tell it how hard to try or how much of a suggestion. We decided not to use it in the end because it kind of felt like you were sort of forcing our perspective on what the lived experiences of other people were, but it's a cool feature.
Yeah, just related to this question, so just remember that there's one example of a mathematician, Boolean, like he found that human emotions are very hard to predict.
Yeah.
So he tried to write down a mathematical formula to predict a human emotion, obviously,
Yeah, yeah.
right? Because it's based on the
Probably
person's
wasn't on the
data.
graphs
Like,
and
he
the
wasn't
results. Yeah.
predicting your emotion. How can you write a formula?
Yeah,
about
for
it?
sure.
So I think for me, I'm being very curious to know about how they look at like human unpredictability. Like there's one example of like, I don't know, I remember there's a family member loved eating ice cream during winter time because for them it warms them up. Or then like, I don't know, having coconut milk when it's hot. Like things like this.
So zero shot, like you can tell it how much of a session to take. So you can say like, these are my cluster names, only find stuff like this. Or you can be like, hey, here's some suggestions. And so what it will do is it will do all the clustering without zero shot. And then when it gets to the representation stage, it will go like, do any of my clusters look like they would be well represented by the word coconut or whatever? So you can kind of give it nudges, as opposed to being like, only look for people mentioning blankets or whatever.
So those are very good, like how would you be able to look at outliers and things like that?
I mean, you still get the outliers from the clustering, right? So,
Okay,
but it will, the way it works is it doesn't, so you almost do topic modeling twice, once where your representations are the zero shot words and once without. And so you end up with an output where some of your representations are like nice sentences or nice words you've written, and then some of them are like hodgepodge together ones that I showed you, like.
Okay.
Cool. But yeah, I guess, and then there's the important slide at the end with the. Wait, is that? Cool. Yeah. The GitHub's work in progress, so don't like. I mean, like the code will run today. So if you want to look at any of the code, it's all in a public repo. If you want to learn Python or anything like that, the JGI helps run some. There's some resources there. If you want to ask me about anything else, it's my email. If you wanted free data science help, there's Ask JGI. And yeah, thanks for having me. Cool.
Great, yeah.
Hi.
Good overview.
Yeah.
Anyone online with any questions?
That's a shake of the head from Ellie.
I'll stop recording.
Okay, thanks. Where is it?